The topic is factoring, and we are specifically going to be looking at factoring by using the greatest common factor. So what is the greatest common factor, or the acronym for greatest common factor is GCF? Well, we're going to define it as the largest common combination of integers and variables that we can take out from some set of numbers. Let's bring us back down to some middle school mathematics. We know that if we tried to find the greatest common factor between two numbers, we could take that down to something called the prime factorization. Okay, and so prime factorization is where we take two numbers and bring it down to all of the prime numbers that it is multiplied. 36, let's start with this number. 36, well, I don't know what all the prime numbers are that multiply to 36, so I'm going to start by saying 36 is 9 times 4. And I can break that down and say, well, 9 is 3 times 3, 4 is 2 times 2. So if I were to write that prime factorization, I would go from the smallest number to the greatest factor. So I would say that's 2 times 2 times 3 times 3. Likewise with 24, well, I know 3, that prime number goes into 24, so I broke that down as 3 times 8. Then I said, well, 8 can break down further, so I did 2 times 4, and then finally 2 times 2. So all of my prime factors are at the bottom of these branches. 2 times 2 times 2 times 3. That would be the prime factorization of 24. How is this going to help us? Well, this is going to help us because now we can compare these two prime factorizations to find the greatest common factor. Okay, so now we want to find the greatest common factor. So I'm going to say that 36 in its prime factorization is 2 times 2 times 3 times 3. Likewise, I'm going to say that 24 is 2 times 2 times 2 times 3. Well, what common factors do we have between these numbers? 2 is in common, another 2 is in common, and a pair of 3's are in common, meaning 2 times 2 times 3 is in common, which is 12. So the greatest common factor, the GCF of 36 and 24, is 12. Now we could look at what are the greatest common factors of these sets of numbers, 42 and 90. Well, I'm going to make a prime factorization tree. Okay, I just created my tree, and in looking at it, here's my prime factorization tree for 42, I mean. 42 has a 2 times a 3 and a 7. 90 has a 3 and a 3, 2, and a 5. So I've written these prime factors out. Now, again, I want to find what is that greatest common factor. That would be there's a 2 and a 3 in common with these numbers, and that's it. So the GCF of 42 and 90 is 6. What about 9, 10, and 30? Well, let's look at 9 and 10. 9 is 3 times 3. 10 is 2 times 5. There's nothing in common between those two in terms of their prime factorization, so that means there's nothing in common for the entire set of numbers. No greatest common factor other than 1. We're going to use the same concept of finding the greatest common factor when we have integers and variables. For example, 12x squared and 20x. What is the greatest common factor? Again, I labeled out the factors of 12x squared. The first one there is 12x squared. That's 2 times 2 times 3 times x times x. Same with 20x. I labeled what those factors are, and the factors are 2 times 2 times 5 times x. I have circled what's in common. 2 times 2 times x is in common, meaning 4x is our greatest common factor. We can look at this with numbers and variables that are a little bit harder to see. For example, 36x squared y cubed and 24x to the fourth y squared. Again, I've written out 36x squared, there's 2 x's, y cubed, there's 3 y's, 24, x to the fourth, you can see 4 x's, y squared. Circling what's in common, I have 2 times 2 times 3, x times x, y times y. So in writing that out, 2 times 2 times 3 is 12. X times x is x squared. Y times y is y squared. So our greatest common factor is 12x squared, y squared. But how can I do this, finding the greatest common factor, without writing everything out? Well, what we need to notice is that when we look at x squared, let's compare just the x squared variables for both of them. We have an x squared and an x to the fourth. And what became the greatest common factor was the smallest exponent, x squared. Now let's compare the y's. I have y cubed and y squared. What became the greatest common factor? The y with the smallest exponent, y squared. That's because when we're taking stuff out, we want to take out what is most in common. We can't take out more. We couldn't take a y cubed from this term because we do not have 3 y's. So using that principle, let's look at finding the greatest common factor of the following 3 terms. I'm going to start by comparing the s's. I have s to the 8th, s to the 5th, s to the 12th. Again, I could write everything out, but I'm going to say all of them have s to the 5th in them. So s to the 5th is the greatest common factor of s's that we have in this term. Now looking at our t values, t to the 14th, t to the 21st, t to the 31st, t to the 14th, that is the most amount of t's that we have. So s to the 5th, t to the 14th is our greatest common factor. So now that we can find the greatest common factor, we need to figure out what is left after we factor these out of expressions, such as 8m plus 24. Well, you can see in red the greatest common factor in this case is just 8. And left over in black, we have m plus 3. So when I take out that greatest common factor of 8, this would be simplifying through factoring, I'm left with m plus 3. To check, we can distribute by saying 8 times m and 8 times 3. 8 times m, sure enough, is 8m. 8 times a positive 3 is a positive 24, and we are back to our original expression. All right, let's try a little bit more difficult one. So 35a cubed b squared minus 14a squared b cubed. We're trying to find the greatest common factor. Well, the greatest common factor is 7a squared b squared. That is the largest set of numbers and variables that can come out of both terms. So what's left once we pull that greatest common factor out? Well, you can see in red is the greatest common factor and black is what is left over. We would rewrite that as the greatest common factor times the quantity of 5a minus 2b. So a little practice here at the end, factoring out the greatest common factor. 6f plus 36. Well, it's important to notice that there are no variables in common between these two expressions, but there's definitely a number in common. That number is 6. So I'm going to factor a 6 out of both terms. If I factor a 6 out, that means I am left with an f plus 36. I can think factoring out is kind of like dividing. Okay, so 36 divided by 6 is 6. So I have 6 times the quantity of f plus 6. This next example, y to the 6th minus 10y to the 4th minus 3, or y to the 3rd power, there are no numbers, coefficients in common, but there are variables in common. And what is the greatest common variable? Well, again, we're going to look at the exponents, and I see that y to the 3rd is the smallest exponent. So I'm going to take y to the 3rd out, leaving what is left. Y to the 6th would be y to the 3rd minus 10y. Now it's important to note when I take y to the 3rd out again, it's almost like dividing it from each of those terms. Y to the 3rd divided by the y to the 3rd is 1. So do not lose that last term of 1. And that would be your greatest common factor.